Welcome to part 2 for our 1.4 section matrix multiplication and of A times B and then C times R. In the previous video, we focused on A times B, so multiplying matrices together, matrix to matrix multiplication. I want to look backwards. This video and the following video to round out this unit and this lesson is really now focusing on the multiplication of C times R. And this lesson is mostly going to focus on where C and R come from, as well as how we find C. And essentially where we'll end is kind of the logical question of then, well, how do I find R? And that's what we'll do in the next lesson. So hopefully as we're digging into these problems, you yourself kind of start to ask that question, well, where is he getting that R from? Why is the R that? Because I think in this first problem, it can be a little misleading in where the R comes from. And so I'll kind of highlight that a little bit, especially if you haven't looked at the notes or looked at the textbook in this problem. So one of the things to keep in mind from 1.3 and where we kind of begin at is rank 1 matrices, is that rank 1 matrices have one independent column, but we also found out that they also have a row rank of 1, meaning that they have one independent row. And this first matrix, which is a 3 by 4 matrix, notice has only one linearly independent column, and that's the very first column, 1, 3, 2. And so the column space of A in this example is one single vector, 1, 3, 2. And so thus it has a rank of 1. Now, it also turns out that if I compare the rows like we did in the third lesson and started to look at the ranks and the row rank versus the column rank, is that each row is a multiple of the first row. Notice that this row is 3 times the first row. This row is 2 times the first row. So this means if I wanted to look at the row space, that is constructed of the row 1, 2, 10, and 100. This then also has a row rank of 1 so that they were equivalent. And in the previous lesson, we started to investigate specific cases of 2 by 2s, 3 by 3s, and try to start formulating that early theorem of if a matrix has a column rank of R, then the row rank of R of that matrix is also R, that it always comes out to be the same. Well, what we're going to ultimately do here is in breaking this down, if the column space is 1, 3, 2, what if we equate this to 1, 3, 2? And notice how this matrix is essentially a 3 by 1 matrix. It's a single vector column because there's only one independent column here. Well, if I multiply this by the row space that we found, 1, 2, 10, 100, which is a 1 by 4 matrix, the result then is a 3 by 4 and is actually exactly our matrix of A. If I take 1, this row, and I dot product it with each entry here, then that's going to give me each entry in the row 1, column 1, 2, 3, 4. If I take my second entry, number 3, and I dot product that with each column here, then that's going to give me row 2, column 1, column 2, column 3, column 4. In other words, matrix A can be broken down into the linearly independent column and then another matrix R. And this is what I was kind of alluding to, that in the textbook, the way that he labels this and the way that we will look at this is in terms of C times R, where C is going to represent all of the linearly independent columns. I was thinking about calling it like a collection of the linearly independent columns. Specifically, it is the collection of the R independent columns. If we let R again represent the rank of the matrix, remember the rank is counting the independent columns. So if I take those first R linearly independent columns and I put that into its own matrix, we call that matrix C. Well, to get back to the original problem then of A, that original matrix, we need to multiply this by another matrix, and we call that R. And this capital letter R, it feels like C stands for column and R stands for row, but that's not necessarily the case. And so I just want you to be very, very careful. In a lot of textbooks, capital R stands for upper triangular. And so forming an upper triangular matrix. just as kind of an FYI. So just be really careful there that C here doesn't necessarily mean column or column space. R does it not necessarily mean rows. It is just the notation that we're using to represent what I would call the column space, so that matrix created by my linearly independent columns, and another matrix R where we want to multiply those two things together. Now, he gives a comment later on that in chapter 1, our objective is to figure out what C is first, and then we'll find R from that. Later in chapter 3, and just the way that he has organized this material, we will focus on finding R first. And we'll figure out how to find R first, and we'll find out again that it will essentially equate to an upper triangular matrix. So what this example is essentially showing that is if I have a rank 1 matrix, we can break it down into this factorization of C and R. But what happens if it's not a rank 1 matrix? What if the rank begins to increase? Can we begin to start to generalize this as R independent columns, and then that number of columns in the original matrix here? Essentially the idea is that notice how these numbers would essentially match. If rank of a matrix is 2, so say it's a 3 by 2, then this would have to be a 2 by 4. And so we would have 2 rows. So the column rank would essentially give the row rank, how many rows I would have in R when we're labeling and kind of measuring these things out. Now, if the column space of A is a line, the row space of A is also a line. This is a thing that we've talked about in previous lessons, so I'm not going to harp on that too much. Instead, I want to turn to the next section, essentially on page 30 of the 6th edition, is we're going to focus on C. How do we find C? In this video, the focus, in this part of the lesson, it's all about finding C. And so how do we find and collect those first R linearly independent columns? And so to do this, this is actually a procedure that we've been practicing pretty much the entire unit that we've been talking about linearly independence. And he gives a step and procedure in the textbook, and I'm going to reference it. I'm not going to write it up on the board because you can clearly read it or see it in the teacher notes. The idea is starting with that first column and then going through and checking each column against any previous linearly independence. And the algorithm just says to continue to keep going. So you do this until you've checked every single column, and then C is the matrix containing all of those linearly independent columns. And so he gives an example, and I'm just going to start with that example of A being 2, 4, reading down the column, 2, 4, 1, 6, 12, 3, and then 4, 8, and 5. And so when I'm looking at this matrix, another comment that will be made in the textbook, and just to go ahead and reference it now, is that because of the method that we're choosing by going from left to right, because we're starting with this first vector, this column vector, this first column is always going to be a part of C. So I can almost go ahead and begin to construct my matrix for C by filling in that first column. And notice that as I go immediately into the second column, we see that the second column of A is dependent on column 1. If I multiply this vector by 3, we create the second column here in matrix A. So this second column is not independent. If I move to the third column, we can kind of see that there is no multiple of the first one to create this one. It appears from the first 2 entries that it could be a multiple of 2, but that last entry, notice, will not work with that. The other thing to kind of notice is that because this second column is a multiple of the first, it lies on the same line, then this has to be a completely new vector if it's not a multiple of the first. If this is along the same line, then the addition, there's no linear combination here. Any combination of these 2 vectors is going to stay on the same line. So if this doesn't work into that one, there's no way we can add this and still get to that. So that's why the book doesn't really talk about or focus on the linear combinations using this one, because it's a part of that same line structure created by that first column. So my C matrix is essentially being constructed then by the first column and the last column in my original matrix for A. And this is where it gets essentially kind of interesting, because you'll notice that A is a 3 by 3 matrix. My matrix for C, which represents essentially the column space for this matrix, is a 3 by 2. So that means if I'm going to try to factor this into C times R, so 2, 4, 4, 8, 1, 5, again being a 3 by 2, I have to multiply this by a 2 by 3 to make the dimensions work in terms of my resultant final matrix. So we need to try and figure out what this matrix is, and that matrix then is going to end up being my matrix for R in terms of that factorization. So we need to figure out what it is. Now to try and determine what that is, we need to start thinking about, and this is kind of getting into the next section of matrix multiplication, the C times R. We need to think about which columns were independent and which ones were dependent. We know from our previous lesson with the permutations of swapping columns and swapping rows, we do that by multiplying an original matrix by the identity matrix where the rows and columns have been swapped accordingly. That'll make the respective changes to the original matrix. Well, it's the same idea here. If I want to create the same column in A that I see here in C, then the first column that I have in my matrix for R needs to be 1, 0, or 1, 0, not comma, apologies. So when I go through and I do this multiplication of row by column, notice how this is always going to print off the first entry in each row here, which then will construct the original column in matrix A. Well, because this is out of order, like my linearly independent columns aren't sorted, because I have this dependent column in the middle, we actually don't know what that second column is in R. I do know that the third entry keeps this column where it's at. So 485 needs to stay the same. Well, because it's a 2-column matrix, the entries here by row will be 0, 1, because I need to make sure that when I do my dot product, this 4, this 8, and this 5 go unchanged. We need to multiply by 1. I don't want any extra addition. So it's a similar argument, but notice how the placement of my 1s and 0s have been swapped, because here I want the 1 to match these numbers in the first column. So that means it would be placed in the first row here. The last column, the third column, 0, 1, matches with the second column in my matrix for C. Our task now is to figure out what R is. And this is why I wanted to mention earlier that hopefully as you walk through this big question that you should ask is, how do I find R? Like, how do I figure out what those question marks are? Because there's an example a little bit later that I think is going to be hard to see. Because in this case, we already saw why the second column was linearly dependent. If I go back to checking this, remember that multiplying this first column by 3 gave me the second column. So if in R, this is the representation to construct the first column, to make it 3 times that, I need to follow this format. But instead of a 1, we want to multiply that first column by 3, and I want to multiply that second column by 0 because there's no other addition needed to construct that middle column in A. And so what we have now found is my matrix for R, which is 1, 3, 0, 0, 0, 1. This has a rank of 2. That has a rank of 2. And so we have found our 2 matrix multiplications for C and R. That would construct ultimately my matrix A. Now this example, he gets into essentially discussing some descriptions of C and R. For example, C contains the full set of R independent columns, but they are chosen very specifically from left to right in A. In part 2, one of the things to identify, and this is where things can kind of get a little confusing in terms of the way that the wording is and the math notation, so I'll try to best fill in as I can. When you look at the matrix for R, I want you to notice in terms of a 2 by 2, focusing here and here, those 2 columns are the 2 columns of the identity matrix I. So R contains I. And so one of the ways that we can think about R is by defining it as I times some other matrix F, where I is going to identify where my independent columns are in A. F is going to identify the combinations that produce the dependent columns in A. But more importantly, if I'm treating R this way, where my I comes up front, remember I in this case for a 2x2 would have to be 1, 0, 0, 1. But that doesn't happen here because the 3 zeros in the middle. That is because my independent columns are not in order. Because this is dependent in the middle, it's causing the way to think about R in terms of this definition to not make a ton of sense without some kind of permutation and swapping columns and swapping rows, which we'll get into a little bit later and kind of see a little bit later. So I think the formalization here can be a little confusing. And so just to specify some important things, just in terms of how he's defining this. Now the dependent columns of A are combinations of C times F. And this is what I kind of mentioned before, but to see it, I want to kind of go back to the general notation, especially with what we have on the board, that if we're going to call A as equivalent to C times R, if I replace R with IF, a matrix containing the identity in another matrix F, if I distribute this, notice the format that it creates is that the independent columns, so essentially A is constructed of the first independent columns of C, and then the dependent columns are constructed according to this linear combination decided by F of the independent columns, because that's what makes them dependent. This holds all independent columns. This contains the linear combinations of those. I'll just say linear combos, and my writing's kind of scratchy, so I apologize. But it's the linear combinations of those independents, aka it's giving you the linearly dependent columns in A. But this is only true if they're in order. And so you kind of see that mentioned in parentheses when he's defining this. So if your independent columns happen in order, then my R matrix can be broken down in terms of the identity times some function F, and then we're just trying to identify what that function F is. And we have to approach it in terms of finding that linear combination. How do I get to those dependent vectors? How do I know that they're linearly dependent? And then filling a matrix to give those combinations. And so let's just say if I was to swap these two, so instead this matrix became 4, 8, 5, and then 6, 12, 3, then my R, you'll notice, would swap these two. So I would have 1, 0, 0, 1, but then 3, 0. This is my identity matrix. This would be my F. My F would contain the linear combinations, essentially multiplying just the first linearly independent column by 3. That would construct it. And so this is what he's kind of getting into when he's making those definitions and breaking it down in terms of that 1, 2, and 3 on page 31. How he's labeling it out. So just something to kind of remember. A little bit reinforced in equation 11 in the textbook when you can see a rank of 2. When a column of A goes into C, a column of I goes into R. So just something to kind of point out. If all columns of A are independent, then C is equal to A. What is R? It's the full identity matrix. If all three of these columns are linearly independent, then R is just I. This would be a 3 by 3, which means I would need to multiply it by 1, 0, 0, 0, 1, 0, 0, 0, 1 to construct. We're essentially saying 4 is equal to 4. What do I multiply with 4 with to get itself? 1. The identity matrix represents that multiplication of 1. And that kind of gives us, at the very big top of page 32, he gives an informal proof for the row rank equivalent to column rank. So I'll let you read through that. And then as well in the box, you will kind of see an example of a of a 2 by 4 being broken down into CR. And we can take a look at that. So I'll write out that example. I'm gonna grab an eraser. Just to, I think, kind of reinforce the following piece of the lesson, which is, how do we find R? Because again, and this is where it's mentioned in the text, and I had kind of mentioned at the beginning, that our process right now centers around finding C first, and then we find R based off of those linear combinations. Later on, we're going to find R first in chapter 3. So if I have a matrix A as 1, 1, 2, 2, 3, 4, if I remember right, and then 4, 5. When I'm doing my check to figure out what C is, I'm going to start with the first column. So C, I know, has to have a 1, 1 in it. We see that the second column is a combination of the first. If I double this vector, I get this column. So I know that this is linearly dependent. This vector is completely different from the first because it's not a scalar multiple. So I know that I have at least a rank of 2 in this case. And it turns out that this last column is linearly dependent as well. And this is where I feel like it's not as clear in terms of the combinations and how to find R that way. Because you would almost argue that, well, actually, this one is kind of clear. I think it was a previous example that I was thinking of. Because what I can do is if I take a look at my 2 independent columns, notice by adding them straight up, we get this one. So it's actually not terrible. And so if I wanted to break this down, I would have 1, 3, 1, 4. And then my matrix for R, if this is 2 by 2, and we're supposed to get a 2 by 4, I know that this R has to be 2 by 4. Because I want to put 1, 1, and 3, 4 is in C, and I want to put these in column 1 and column 3, that means in R, this is 1, 0, and 0, 1. We need to figure out what these entries are here. The second one is really easy. We know that I would multiply only the first column by 2. So that means, like we saw before, this would be then 2, 0. This would multiply just this first column by 2, multiply the second column by 0. To construct 4, 5, we mentioned it earlier when I came to the realization that it's pretty evident. If I'm adding these 2 vectors together, then it's just going to be the first and the second added. We just need 1 copy of each. So that means this last column is 1, 1. And thus we have our C and we have our R matrix. That 0 is bothering me. And so I can put that there. And so notice again, C has a rank of 2, R has a rank of 2, and listing that out. And that finishes us out with this video. We haven't, again, really seen how to calculate R, and so that's what the next lesson we'll get into. Big ideas of this one is to identify C. We need to identify what my linearly independent vectors are, independent columns in A. And to do so, we're always going to read this from left to right. We're looking for those linear combinations. My matrix R contains all of the linearly, essentially the combinations to construct A from C, doing the matrix multiplication. The rows of C times the columns of R, or essentially the matrix C times each row, each column. Let me know if you have any questions, and check out the next lesson when you're ready to determine how to find R.